So, you guys know about the rock stars like Bono and Cher, you know, only known for one name, Madonna, right? Well, our next engineering rock star is known only by the name Regu. He's Vice President and Global Head Engineering and Industrial Services Unit at Tata Consultancy Services Limited. Regu holds a master's degree in mechanical engineering from the Indian Institute of Technology in Madras, India, and a bachelor's degree in mechanical engineering from the University of Madras. And Regu is all the way here today from India. Would you please help me welcome the engineering rock star, Regu.
If you know the words, please help us sing along.
Morning. I'm not sure I'm a rock star or something, but at least I will try to do best in terms of talking about connected digital enterprise for the next 15 minutes. There has been a lot of sessions on this particular topic in the last 4 days in this PLM world, especially around digital thread, digital twin, and all the associated technologies around connected digital enterprise. I think the good thing today, connected digital enterprise is not a topic that is getting opened up. It's not like it is going to happen in the future. It's here and now, and we are facing it, and we have the tools and the technologies to implement it, and we are seeing number of business use cases coming up in terms of how this connected digital enterprise can help accelerate the transformation within the enterprise. I have some initial thoughts around how this is being implemented across many of the industries and the use cases that are potentially coming up and being addressed. And also I have a few case studies where this has actually been implemented, both from a digital thread perspective as well as from a digital twin perspective. And I will kind of give you a quick glimpse of all of these cases as well. If you look at the connected digital enterprise, as I'm not going to spend a lot of time in trying to define the connected digital enterprise because many of you would have gone through it already. So it kind of connects multiple functions within the enterprise so that we are able to get a real state information about a product, process, and the performance of the entire value chain. It's very important to look at this from value chain because many times we try to construct a connected digital enterprise in a very siloed or subsystem manner. For example, people think that if I can put some sensors in my product and collect the information about the performance of those products, that essentially give me a connected product or connected system. But that particular solution alone does not address the connected digital enterprise concept, because you will be unable to use that information that you collect from the product, from its performance, to make any decisions with reference to its previous life cycle stages. For example, in design, for example, in manufacturing, for example, in planning, for example, in traceability. None of that can be used because you don't have a connected digital enterprise solutions. So I would like to stress that when we are contemplating on a connected digital enterprise, it's about the whole value chain. The complete value chain have to be thought through, and the way we really integrate those systems and the informations, both real-time information, design information, and manufacturing information, have to be providing that complete value chain view. We are now seeing number of interesting use cases are coming up in the industry. There are many. I have just listed 5 of them there. And across many industries, whether it is in automotive, whether it is in industrial machinery, in medical devices, in pharma manufacturing, in CPG. So we see these use cases coming from multiple industries. So if you look at, for example, the first use case, the product performance insights for design enhancements. It's a very interesting thing because we worked with one of the automotive manufacturer out of Japan. They have fitted with number of diagnostic devices that they supplied to various service dealerships across the world. And each time you take a car to the dealership, the service dealership put that device and get the diagnostic trouble codes out of the car and use that to address any issues that may be there in the car and fix the problem and provide the car back to the owner. But at the same time, the data that is getting collected is now coming as part of this connected digital enterprise into their cloud, where we collect the data from close to around 15,000 dealerships all over the world. And you can imagine over a period of last three and a half years since this system is in operation, how much of data that would have been collected. And the use of that data, when we start providing the insights, is very many. So today, one of the use of the data we do is look at the data of what kind of diagnostic trouble codes that have been reported, and we categorize according to the models and the make of the year of the car, and we look at across the whole gamut of platforms. They have the automotive companies have those platforms, and feed that back to the design engineering so that they know exactly how that product is performing in the field and they are able to take corrective actions. So that's a case study live in the operation for an auto industry, which is product performance insight for design enhancements. If you look at manufacturing, at the plant level, it's going through humongous changes. Industry 4.0, as we all know, or smart manufacturing here in the US, is quite a common thing, and everybody is implementing systems. And very ubiquitous item like energy, for example, is measured in terms of how much of the peak load demand you actually utilize in the shop floor. If you are operating a heavy load machines together, like a press shop or any of the shaping machines, it actually adds to the peak load electric power requirement. And when the peak load is higher, your energy bill also goes higher. By sequencing the manufacturing operation into a way by which you don't operate these machines together or start those machines together, people are actually moving from a passive energy management or energy optimization technique to an active energy optimization technique. So from passive energy management to active energy management. Because we have that information, because we can feed the information of manufacturing sequencing and the scheduling from the planning system and the MES back into the shop floor systems, we are able to tweak how these machines are operated, and that results in significant saving in the energy consumption of that. That's just one example. There are a number of ways this Industry 4.0 is bringing efficiency at the shop floor. There are also a lot of examples coming up from supply chain, real-time supply chain visibility perspective. We work with number of CPG industries where the availability of the goods on time and the logistics and transportation is key, especially with the perishable goods. And today we have IoT-based systems that have sensors on those trucks or the trailers, and we are able to track the temperature, moisture content, and the humidity levels. So a lot of parameters are being tracked in order to deliver that particular good in a fresh state to the end customer or to the store. So there are huge number of such use cases are coming, and today the realization of connected digital enterprise is really helping these companies to realize that benefit of putting these systems into place. Moving on, what are all the key elements and the characteristics of this digital enterprise? The fundamental thing is it kind of provides state information, process information, and the performance information on real time. So whether it is design, engineering information, or whether it is manufacturing planning, whether it is actually the performance data or as manufactured condition data or the quality data and test data, we are able to see that. And digital twin provides an opportunity to represent that physical asset across the value chain. I'll give an example of this. And today, the ability of the IT infrastructure we have, whether it is cloud, whether it is big data, is able to provide a very integrated view of the data we have, which has always been a challenge in the past because we had PLM data, we had MES data, we have shop floor data, sometimes commissioning data from the field. None of that could be integrated because of the way it has been part of the enterprise in different locations. Now cloud provides the ability for us to collect the data, and as well as big data provides the ability for us to process that in a structured manner. And there are a lot of methods that are coming, and we are able to unleash the power of analytics to unravel this data into useful insights. So when I talk about analytics, it's not just the part of information that we apply in terms of standard machine learning or any of those analytics. It is also about analytics connecting the product information, the physics of the product, the physics of the process, and the engineering around it, along with the data we are collecting. So it's real-time data, performance data, plus the simulations and physics data that we are able to get. Combining all this, we are really able to unleash the power of analytics to make insights. And last but not the least, it's a closed loop system because we take this information that is coming out of the performance and feed that back all the way into the decision-making loop in the engineering. And we are working with, one good example of that, we were working with an oil pipeline manufacturer and trying to set up a digital twin for measurement of the oil pipeline performance. There is sensors around that pipe that measures the thickness of the pipe across, say, around 800 miles, 600 miles, 1,000 mile length. It has at various intervals. And these mods collect the data from the pipe and able to bring it to a cloud where the thickness is constantly measured for various periods of time. And one of the things that customer was trying to do is if the thickness level due to corrosion reduces to a minimum threshold level, then that basically signifies that that particular pipe is leading to a point of failure and they have to take some replacement action or preventive maintenance or predictive maintenance. But it's not that just the measurement and the reporting of the thickness, but if you are able to combine that with the physics of the pipe, on that particular thickness, how much could be the pressure that can be allowable, that is connect that CAE information or simulation information into that. You don't have to go and change the pipe. You can actually take a different decision that I would let the flow inside the pipe to be at a lower pressure than I have planned it for. So in that case, the maintenance schedule can be completely replanned instead of just go and replace the pipe. So that's the difference between using just real-time information, but with the physics, you can have a completely different view of the problem. That's what we mean by the closed-loop system decision-making. So we all know about the digital thread. It's connecting all the engineering, manufacturing, and a number of systems, not only in the shop, but also at the field at the service level. Key information about the product, key information about the process, as well as the product performance is collected through this. But I think the most important and most helpful thing in this is it is very persona-based. You are able to provide information based upon each persona that you are addressing here, whether he is a quality engineer, whether it is a design engineer, or I am a commissioning engineer, I am able to see this through the persona-based systems that we are able to get here. And we implemented this digital thread for a thermal power plant manufacturer, and it's quite an interesting implementation connecting all the way. At the bottom, you see the IT systems that combine design, manufacturing, and the service management systems, all the way into the shop floor instructions, and the whole pillar of performance analytics using remote diagnostics and getting the data of the turbine and the various items inside a plant back to the organization. It's provide a huge benefit in terms of increasing their inquiry to order process, reducing their OTR failures or delivery slippages, and as you see, addressed almost 60% of their complete non-conformance that was there. And it also provided a huge benefit because a lot of time between manufacturing and design information flow due to paperwork as well as due to various ways, there is a lot of disconnect and gaps. Today, it is a single system, and what we see in the engineering is seen by manufacturing. And not only that, what is seen in the manufacturing as is manufactured condition is seen by the commissioning engineers. Remember, in a heavy duty equipment like a turbine, when you do a commissioning, and if you go by the design information and design drawing information and trying to commission it, but the manufactured condition is different, it causes huge delays and reworks. Now we are able to address that. What is manufactured is relayed to the commissioning engineers so that they are prepared from the commissioning perspective. I have just one small case study before I close. We created this digital twin for a 600 megawatt boiler, and many of you are aware that thermal power plant boiler is a huge complex piece of equipment, close to the height of around 280 feet. And it has number of sensors, 2,500 sensors, systems, and various inputs and parameters that one has to tune. And typically when you tune the boiler for heat rate performance, which is how can I get maximum thermal output and the power output, then it degrades the emission performance. When you go and optimize for emission performance so that I can reduce my COX and SOX emissions, it degrades the thermal performance. And 1% of thermal performance is close to around $5 million per year for the boiler utility company. So in this example, what we are showing here, we created a digital twin. We modeled the thermal performance of the boiler. We took 6 months historical data of the boiler and created an artificial intelligence machine learning model on top of that data. So the physics-based model and the artificial intelligence model has been validated on the past data. Then we went to this actual site, field site in Taiwan, and we collected the data directly from the control room into this artificial intelligence engine, optimized the parameters for a period of 7 days, and that yielded in significant improvement in the boiler performance, at the same time meeting all the emission norms. Typically, this is done by commissioning engineers through trial and error, and never you will be able to realize whether you reached that optimized point or whether they leave it because they got to some level of optimization and they just leave it. And it takes around 14 to 15 days of tuning operations for those engineers. You can see the number there. But using this kind of digital twin model, they were able to reduce the time by more than 30%. Not only that, they were able to reduce the fuel burn as well as optimize the heat rate of the boiler. So in conclusion, there is quite a lot of happening in connected digital enterprise. People are investing both on digital thread as well as on digital twin. If I have to put a kind of roadmap for organizations to take on this journey of connected digital enterprise, let's work on in terms of getting the data at the enterprise level, especially within as well as the connectivity of the equipment at the performance level as well. The tools that are available for diagnostics as well as for creating analytics and insights are very immense, and invest on driving decision based on those analytics, but don't forget about we have to connect closed loop with the physics of the equipment or the product. And I didn't talk about this in this presentation for want of time. There a whole lot can be done by enhancing the user experience using technologies like augmented reality and virtual reality. Today, for service engineers, maintenance engineers, that is a big boon in terms of actually be able to do these things very effectively and make those processes and procedures for complex equipment through these technologies by AR and VR. Thank you very much for this opportunity, and thank you again.